All right. Thanks, guys. All right, non-smokers. According to the Center for Disease Control and Prevention website, 50% of high school students have never smoked a cigarette. Taeyeon wonders whether this national result holds true in his large urban high school. For his AP Stats class project, Taeyeon surveys a simple random sample of 150 students from his high school. Yes? Well, can we go? So he surveys 150 students from his school. He gets responses from all 150 students, and 90 say they've never smoked a cigarette. What should Taeyeon conclude? Give appropriate evidence to support your answer. All right. When you write your null and your alternative hypotenuse or hypothesis, that's mathy of me. Hypothesis. Make sure that you guys don't look at the p hat. All right. Don't look at his survey at all. You don't care about that result when you write the null and the alternative hypothesis. So H naught would be that our p-value is 0.5, 50%, right? That's according to the CDC website, all right? The alternate, we didn't have any kind of speculation. So if they say that Taeyeon or whoever has some sort of speculation that it's greater than or less than, that's when you know it's a one-sided test. If they don't give any speculation, you have to just say it's different from 50%, okay? So not 50% would be our alternate hypothesis. Where P is the true proportion of teens who have never smoked. What else do I have to do in the state part? There's one more thing we have to remember to do. Yeah, Maddie? Yes, what is it called though, you guys? Significance level, but yep, because before it was confidence level in the last part. We want to do this at a significance level of alpha is 0.05. Yeah. Yep. Yep. And we do 0.05 if they don't tell you. All right, so we're going to do a one sample z-test for proportions, same as before, because we're still talking about 0.5, a proportion. And we have to go through all our fun stuff. So did we do a random sample? Yes, we did a random sample. Random. Okay. And we have to check 10%. So he gets responses from all 150 students at his large urban high school. So we would say that means we have at least 1,500 students in the building. I don't know what that was. All right. You can write it as 150 is less than or equal to 10% of all the students as well. Same thing. Okay. And then we have to do n times p and n times 1 minus p, except for our p this time is what, you guys? Okay, it's 0.5. It's the p null. That's what we're comparing it to. So we're going to do n, how many did we do? 150 students times 50% has to be greater than or equal to 10. So that would be 75. So we're good to go there. And the same thing here, because 1 minus p is still 50%, so 75 greater than or equal to 10. We're good to go for large counts. And the fun do part. All right, our test statistic for this one is z. They actually recommend not writing the formula down. I thought that was interesting. Little AP tip. Don't write the formula down on these because people put the wrong symbols. So you lose points for that. Instead, just plug in what goes where, and hopefully you do it right. So we need to find, yeah, so we need to find p hat first. So let's go, Michaela. How do I find p hat? Yes, our p hat is 90 over 150. We'll just write this off to the side, okay? And you got to divide that. You end up getting 0.6. All right, so that goes first, our p hat. And we subtract what we think the true proportion is, 50%. And in the bottom goes our standard deviation, using the true, what we assume is is true. 50 and 50 divided by n, 150, gives us a z-score of 2.45. Now, what kind of test is this? Two-sided. So here's where a lovely picture would help, all right? I recommend drawing this. Doesn't have to be great, all right, but a little normal curve here. That was bad, but 0, 1, 2, 3. It is two-tailed. So even though we only got a positive, you have to do both positive and negative, okay? So two-tailed, your z-score is to the right of 2.45, so about right here, and to the left of negative 2.45. All right, that's new, that's important. So draw both tails when you do these z-scores. Assume plus and minus. All right, and then we need to find the p-value. This is also new, so when you guys do the p-value, you can pick a tail, and what do you think we do after we get an answer? Double it. All right, so times by 2, and a lot of people forget, so please don't forget to multiply by 2 when you're doing the two-tailed test. So our p-value, meaning we want to find, I'm going to do this guy right here, so greater than or equal to 2.45. And so we do normal CDF on our calculator. Our lower bound is 2.45, upper bound is 1,000, mean of 0, standard deviation of 1. Plug it in, and you get 0.0071. I ran out of room, so I'm going to put that right here, 0.0071. And really important, times it by 2. So when you multiply by 2, you get 0.0142. So this would be the area of both of these added together. Okay. So we still have a really small p-value even with both tails there. And so it's less than 0.05, so we reject the null, which means, and be careful on this part, we have convincing evidence that the proportion of all students at Taeyeon School who would say they have never smoked differs from the national result. So don't say greater than, even though our sample was greater than, right? Even though we got 0.6 for our sample, you just say differs, because that's how we do our alternate hypothesis, all right? So that's two-tailed test. Maybe we do this one on the calculator, see if you guys remember it. So according to the National Institute for Occupational Safety and Health, job stress poses a major threat to the health of workers. A news report claims that 75% of restaurant employees feel that work stress has a negative impact on their personal lives. Managers at a large restaurant chain wonder whether this claim is valid for their employees. So a random sample of 100 employees finds that 68 answer yes when asked that question. So is that different from 0.75? Support your answer with a significance test. So you guys go to statistics, right? Stat tests, I think it's called.
Is it okay if we did this on we show
Well, yeah. Yeah, and by the way, you will get a slightly different answer, which is probably why yours is different. You probably used your calculator when you did it. Then if you work it out, it's fine, right? Either way is fine, okay? However, I do want to see how you calculate the z-score and the p-value on your test. So what do you plug in for the null hypothesis when you get to the test? Z1 sample z-test. No, one proportion z-test. So 0.75 is the null, and then your successes are 68, and your n is 100. And then make sure you do the different one when it has the not equal to. I think that's actually the default setting on that calculator. Press OK. And you get a lovely p-value of what? 11%? 0.105. So at a 5% significance level, are we going to reject the null? What do you guys think? Reject or fail to reject? Fail to reject. Okay. Of course, we would go through the whole thing, right? Random, large counts, all that. You guys have gotten hopefully pretty good at that. By the way, your calculator already doubled it for you. So smart, right? So if you use your calculator, that value, the p-value, is already 2 times the probability of that, okay? So they did it for you. Wasn't that nice of them? Okay. All right, so how do confidence intervals relate to significance tests? We need to talk about that for a moment and see if we even remember how to do one. All right, so Taeyeon found that 90 of a simple random sample of 150 students said they'd never smoked a cigarette. We checked the conditions for performing the significance test earlier. Before we construct a confidence interval for the population proportion, we still have to check n times p hat, and n times 1 minus p hat are at least 10. So remember, confidence interval, we actually check with p hat, okay? Because the number of successes and the number of failures in the sample are 90 and 60, we're good to go with large counts. So they did it for us. All right, that was nice. So confidence interval. Raise your hand if you remember the formula that we just did on the last test for confidence interval. Ginger? Yay, good job. All right, so our p hat in this one, you guys, is 90 over 150, which was our 60%. Okay. We're doing 95% confidence, so if you do inverse norm, anyone memorize that z-score? Yep, 1.96, okay. And then plug this in, 0.6, 0.4 over 150. This is going to give us our confidence interval in case you forgot how to do it. So we get 0.522, 0.678. So let's compare this information to the last one. So they said that the null hypothesis was 50%, right? Is 50% in this interval? No. So we would reject that, right? And say we have evidence that that 50% is not true because it's not in our confidence interval. That's what we would have done before. Which one gives us better information? Actually, the confidence interval gives us more information because it gives us a range of numbers to accept versus just saying, is the 60% going to work or not, right? So instead of just that one number, we actually get a range of numbers. One more thing, when you're doing two-tailed tests, these work really similarly. So if I'm doing a 5% significance level, that's going to give you same information as a 95% confidence interval, right? So if I'm doing alpha is 0.01 for my significance test, what kind of confidence interval goes with that? A 99% confidence interval. Make sense? So they give you the same information, and it's only two-tailed tests that this works for. You do have to be able to read these little chart things, mini tab output. All right. So this is a test of p equals 0.5 versus not 0.5. So same thing, but there's our null and alternate hypothesis. So our sample gave us the 0.6. Here's a 95% confidence interval output. At the same time, we got a z-score and our p-value. So right here, we have the range that makes sense at 95%. And right here, we have a p-value that tells us we would reject the null. Gives us the same information. Okay, the 0.5 is not in the range, and the low p-value tells us to reject the null. So the big idea worth considering, a two-tailed test at significance level A would be the same thing as a 95% confidence level with 5%. All right? They give you a little formula, 100 times 1 minus alpha, in case you can't figure out the 1% and the 99%, but it's the same thing, okay? Make sense? So let's answer some questions about the mini tab. If you guys can even read that, it's kind of tiny. It's mini. I don't know if I can make it bigger. All right, explain how the confidence interval is consistent with, but gives more information than the test. So this time we've got P is 0.75 versus not 0.75. Here's our interval. For those of you who can see that, is 0.75 in that interval. Yes. Okay. And for those of you who can see this p-value, is that a 10%? Okay. It's like a 10%. So we would fail to reject the null. So it gives us similar information. But we get better information with our confidence interval because it gives us a range of numbers that work versus just saying, yep, 75 works. Okay? So same thing. There we go. That's it for that. All right, type 2 errors. So this is important. Try to pay attention here. So write down the definition of power. You need to remember what power is. Then power is the probability of avoiding a type 2 error, which is failing to reject the null when you should reject the null because the alternate hypothesis is true. Okay, so power is the probability of avoiding a type 2 error. Okay, so we want to get it correct to reject the null. Yeah, Jake. Right. Right. So the probability of correctly saying that you're going to reject the null. Okay. So for the potato example, back to potatoes, a little safer for those of you that feel safer with this. So the null hypothesis is 8%. That's what we started with, 8%. But let's say we get a truckload and we know it's actually 11%. So we should reject the null. Okay? So how likely is it that we will reject the null? So potato chip producer wonders. Yeah, same thing. All right, so here's our little guy here. And if we've got our 5% significance level, and we shade, so this is the 0.08 in the middle, and there's like more numbers on here, but I don't want to find them all, but you know, they're standard deviations. So here's the 0.05 here, which actually happens at about 10%. So if we get a sample of about 10% or bigger, we're going to reject the null, right? So that shaded region is where we would reject the null. Okay. And so if we do another table, and I want to like line them up-ish. We'll see if we can. So this table down here is at 11%. And I would fill in all the standard deviations and numbers, right? So in the middle is the 11%. That's the true one. And so where we're going to end up rejecting is 10% or greater. So just like this one, it just so happens that 10% or more is where that 5% alpha significance level is. And so if I do 10%, I would line that up with this one and shade to the right here. You never have to actually calculate the power. You just have to interpret the power. Okay? So this right here is actually the power, this shaded region. So this is the probability of you correctly rejecting the null. You might want to draw a little picture on your notes. Okay, and this happens to be 0.76. That's the power. You don't have to ever calculate it, so I'm just giving it to you, all right? So this means that over here is actually our probability of getting a type 2 error. So if I get some p-value over here and I make a type 2 error because I really should have rejected that 8% because it's really 11%. All right? So this probability happens to be 0.24, right? The other end of that. Okay, so correctly rejecting the null. Gives us that power. So the potato producer has about a 3/4 chance of correctly rejecting a truckload with 11% blemished potatoes. That means he also has a 1/4 chance of making a type 2 error. So we want power, right? The more power, the more we're going to do it right, hopefully. Okay? So the closer you are to 0, you have no chance of correctly detecting that the null is false, right? The closer you are to 1, the more likely you are to reject the null in favor of the alternate hypothesis, as you should do. So we've got some symbols for you that you want to make sure you label. So alpha is our significance level, right? Well, if you look back at the picture that I drew, this right here is actually our significance level, right? This is like a 5% significance. That's where we're going to reject the null. And so alpha is actually the probability of making a type 1 error. So it could be 5% chance, 10% chance, whatever your alpha is, right? And a type 1 error is what? Incorrectly rejecting the null. Okay. And beta is the probability of making a type 2 error. So if you look back at the picture, beta is this part right here, 24%. That's the probability of making a type 2 error. So the power relates to that. The power would be 1 minus beta. So if it was a 24% chance of making a type 2 error, the power is 74% that we do it right and avoid making a type 2 error. And the probability of getting a type 2 error is 1 minus the power, because those go together, right? So if you do 1 minus power, you get the 24%, which is the probability of getting a type 2 error, which is beta. Okay. All right, so how to improve the power? How do I make the power better? So to improve the power, you can increase the sample size. Always better to have a bigger sample size. All right, another way to increase the power is to increase the significance level. And I want to go back to this picture to show you why. Increase sample size. So you guys, if I increase the power, that means that I'm going to move this line over. Like maybe now I'm going to do 10%, and so I move this line over. If I move this line over at 10%, I also move this line over, which now gives me more power. Make sense? Hopefully that makes sense. So increase the significance level. Another thing we can do is increase the difference between the null and the alternative parameter values. So if you go back to the picture, if I increase this to 12%, that's going to make it better because it moves this over and gives me more area. All right? Or 13% is even better, 14%. So the further away we are from our null, the better. So it's easier to detect large differences between the null and alternative parameter values. Okay, also we can gain power by making wise choices when collecting data. That's obvious, hopefully, to you guys. Like, the better the sample is, the better the power is, and the more likely you are to do it right. Like, if we were to do everyone that owns a calculator and we picked, like, a certain group of kids, right? That would be a bad sample. So let's make it better that way. All right, so here's some questions about power to make sure you get it. So tune back in. Which is more serious for the potato chip producer in this setting, a type 1 error or type 2 error? So based on your answer, what significance level would you choose? So the type 2 error was where we actually like use the truckload, right? And we make potato chips. So that's worse because if we make bad potato chips, we're going to lose customers and sales, okay? So we don't want to do that. And so which significance level is the best one for avoiding a type 2 error? Ginger. Yep. So this one's the best one because it is the largest significance level. All right. Tell if each of the following would increase or decrease the power of a test. So let's say we started with, I guess, 0.05, and so we changed the significance level to 0.10. What does it do, increase or decrease? Increase. All right. We take a random sample of 250 potatoes instead of 500 potatoes. Increase or decrease? Decrease. We took less potatoes. That decreases our power. So insist on being able to detect that P is 10 or P is 0.11. If we started with the 0.08, right? Which one is the furthest away? 0.11. So we would need to insist on that one, but they're saying we need to insist on the 10 instead of the 11, so that would decrease our power because we would have less of a difference. You want the most amount of difference between the two. Make sense? Okay. Sorry that was long today.